Hello everyone and welcome to our first video for chapter 3. I tend to try to split the videos up just a little bit, that way you don't have too much to watch at once. You can kind of split it in, split your work up and watch the lectures when you're ready. So we're going to cover just the first few learning objectives here. There are more learning objectives for this chapter that you can find in Canvas. But again, I just am going to only cover these 3 in this video. So let's say later on you're going back and you want to study. It's really easy to check like those bullet points on the slides to see what those slides about and like what the matching video is therefore going to be about. So let's get started. And so what we're going to talk about in chapter 3 is matter and energy. So we need to talk about what these atoms are, all the things that make up the universe, and the energy that act upon the matter. So we'll be able to kind of distinguish kinds of matter. We'll define exactly what matter is, what atoms and molecules are. We'll use a few more technical definitions than we did in chapter 1. And we'll be able to classify something as a solid, liquid, or gas. We'll talk about what that looks like at the molecular level. You might be like, Professor Thomas, that's an old trick. I know what a solid, liquid, and gas are, but I promise we're going to get into a little bit more of a technical definition of that as well. In this video, we'll also talk about how to classify matter as an element, a compound, or a mixture. So let's get started. So I just want to remind you that everything around you is made of chemicals. Okay, I didn't know if it said matter or chemicals. Yeah, everything around us is made up of chemicals. Everything you can feel, see, touch, sense, all 5 senses, and that's going to be made up of matter. So there are many different kinds of matter, all the different chemical elements, and then all of the molecules that they combine together to make up everything that we interact with in our daily lives. So I'm using this word matter. What do I mean? Well, matter is anything that occupies space and has mass. So mass is just basically an amount of substance. We usually measure it in grams. You might think when we're using the balances in lab, you might be weighing something, but weighing something has to do with how much gravity is pulling on it, on specifically the Earth. You know, you weigh different on the Earth than you do on the moon. It has a different amount of gravity. However, you always have the same amount of mass. So if I'm here on Earth, I'm here on the moon, I could be anywhere and I would still have the same amount of mass exactly. So matter could be something extremely large like a planet, or an extremely small item like air or dust, or literal just, again, molecules, atoms, those tiny little building blocks of the universe. And matter is composed of atoms that come together to make molecules that, again, build to what we can actually see and interact with our naked eye. Again, there are many different kinds of matter. We'll be talking about lots of different kinds of matter this semester, especially right now in this chapter here. But again, matter is anything that occupies space and has mass. So it's got to have something to it, and it takes up some amount of space. And this is why one of those arguments can be made that almost everything we're going to talk about in this class besides energy can be considered matter, because it's made of atoms, and atoms are matter. They occupy space and have mass. So let's keep moving. So let's again get into those a little bit more technical definitions of atoms and molecules. So atoms are what we call submicroscopic particles, and they're the building blocks of the universe. So when I say submicroscopic, that means I can't walk into one of the biology labs, grab their microscope, plop it down, and look at the atoms, right? I can't actually do that because they're much smaller than what we can see with just a regular microscope. We do have special equipment that allows us to see individual atoms, but again, we're calling that submicroscopic because, you know, you're not even going to be able to use a general science microscope to do this. We'll talk a little bit more about what we do use to do that in just a second. But when I say they're the building blocks of the universe, what I mean is they're like the smallest grouping of stuff that we can like categorize. So atoms are all of the different elements on the periodic table. Those are all the different kinds of atoms that we've discovered thus far when we're looking at the periodic table. And we can distinguish those different kinds of atoms from each other based upon different properties, different subatomic particles they have, so the different particles that make up the atom. And again, we can't tell apart those subatomic particles, subatomic, smaller than an atom. subatomic particles from each other. They could go to any atom. However, I can distinguish and I can tell all of these different atoms apart from each other. So we call those the smallest building blocks simply because it's something that can be distinguished. We can look at it and we can see that we have a different type of Lego, right? Bring it on the Lego bag. So all matter in the end, I mentioned this before, is composed of atoms. So sometimes the atoms only exist with their type of atom. You only have one type of atom. Sometimes they might bond together to form molecules. Sometimes you might have two different kinds of atoms mixed together in a sample. So you can have atoms that sit next to each other that aren't necessarily bound to form molecules. But we'll talk a little bit more about the different classifications of substances, I believe, towards the end of this video. Molecules are at least two or more atoms joined together in specific geometric arrangements. So they're much more complex than atoms are, therefore. They behave differently than atoms do. Molecules behave differently from each other, and we can kind of get some information from the atoms that make them up, how those atoms interact with each other and form those chemical bonds, to think about the shape of that molecule, and then therefore some of the wider and broader properties. But we'll talk about that a little bit later this semester. So there are many different classifications of atoms and molecules, and like the breakdown of this in this classification is kind of really what the root of how chemistry studied is, because you have to know what you're working with and have some information about that before you start working with it or making predictions about what it could do. So I mentioned we have that really, really specific piece of equipment that allows us to see individual atoms. So how do we really know about this? It was a guess for a long time. It was just a theory. We didn't have any actual proof to prove what atoms look like or how we can actually see them. However, we now have what we call a scanning tunnel microscope. So these microscopes are powerful enough to let us see down to the atomic level. So on the left here are some individual nickel atoms. So if you just had pure nickel, this is what the surface of it looks like when we get deep down in it. You know what I mean? Things might appear smooth to our eyes if I touch my desk or I touch my keyboard or something like that. However, it's all of these individual teeny tiny atoms stuck together. For all you biology people out there, and just genuine science curiosity people, that's me, this is actually what your DNA looks like. So this was how we were able to prove that the double helix was what we thought it was, and it was there because you can see that shape, that kind of classic DNA shape running through the molecule here. So this is a bunch of different atoms hooked together here. You can see all the different ridges and bumps. And those are all atoms that are bound together to make this molecule that makes up you and your life. How cool is that, that we can literally see DNA? Super meta that we can look down and see the thing that makes us up. So again, we do now have powerful enough equipment to verify some of these theories. You know, we talked about having hypotheses that can be proven falsifiable. And, you know, we were making guesses, trying to figure out what was going on. And now we have something that kind of proves that, hey, I think I can back up my hypothesis that this is what an atom is and what it does. So I think that's pretty cool. So now we've talked about matter. Okay, cool. Things exist. Breaking news, right? Things exist. But what exactly do we do with matter, and why am I setting you up this way anyways? Chemists and humans love to categorize things. It is like the human condition that we love to put things in categories, that we group things together, and in lots of different things we do. So often science deals with classification to tell different types of things apart. So we're going to talk about states of matter here because this is a way for us to tell different types of matter apart and to be able to think about how they might behave differently if they're in these different states of matter, for example. So we're going to look at a few different ways that you could categorize matter. I've been saying states of matter, but we'll also talk about the type of matter as well. So like what kind of atoms and molecules make up the matter. So we've got kind of two different branches here, two different trees, state of matter versus type of matter, and we can classify the same substance by two different sets of criteria. So Matter technically exists in 4 states. So we're going to talk about 3 in this class, but don't be coming at me in the email saying, hey, Professor Thomas, I know that there are 4 states of matter. No, I know, but there's only 3 that really apply to this class. So the 4 states of matter are actually solid, liquid, gas, and plasma, but usually it's mostly the physicists working with the plasma kind of a deal. So that's like kind of something where everything's kind of floating around in kind of a soupy kind of deal. It's like beyond a gas in terms of how, we'll talk about it, but energetic it is. So you'll understand what I mean by that by the end of the lecture. Like I said, we're only really going to focus on solid, liquid, and gas in this class. So we define the states of matter by how the atoms and molecules are interacting with each other and how much freedom of movement they have, okay? So how do we do some of these definitions? So solids, kind of the basic thing here, you know, my desk sitting in front of me is a solid. The metal that makes up my computer is a solid. The textbook, a solid. They're just kind of, you know, harder substances, right? So solids are atoms and molecules that are packed very close together, very tightly together, and they're always in fixed locations. So they're not moving around too much, okay? So we'll talk about the different states of matter with water because we have different names for the different states of matter with water. So water's solid form is ice, right? So when we're looking at a solid, it's going to look at something like picture A over here, where I've got all of these atoms. They're very tightly packed together, and they're in a rigid structure. So that's what you can expect from a solid. However, we'll talk about this a little bit more in one of the other lectures for this chapter. As long as you have some form of heat, temperature going on, atoms are actually constantly wiggling and vibrating around. So they're constantly sitting there wiggling. So it doesn't look like my desk is moving, but all of the atoms and molecules have these vibrational motions that they sit there and they just wiggle, 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 wiggle. Jason Derulo. But, you know, you sit there and you, they'll wiggle back and forth. So even though these atoms are very tightly packed together, they're within this rigid structure, just wiggling back and forth. So they're going to wiggle and vibrate within the structure, but they're not free to move outside of just that vibrational motion. So it's a rigid shape. It does not change no matter the container. So you can put, you know, a gold ring in a Tupperware container. It's not going to change anything about the gold ring. You could set it on the counter. It's not going to change anything. You could put it in my water bottle. It's not going to change anything about that gold ring itself. It's going to still keep its same shape, and it's not going to change no matter where you set it down, basically. So that's kind of how we're thinking about a solid. Solids are rigid and very, very dense, very, very, like, lots of atoms packed very tightly together. So, in contrast, it'll start to make a little bit more sense what I'm talking about with solids. Let's talk about liquids. So liquids are atoms and molecules that are still very closely packed together, but they can kind of slip and slide past each other. So they're not like breaking free of each other. They're not doing anything else. There might be a little bit of space between the atoms, but they're always just kind of slipping and sliding around. I always kind of think of like the sloshiness of like waves on a lake when I'm thinking about liquids, because that's kind of what's happening. Those atoms and molecules are just moving past each other, crashing into each other, but they're not separate from each other by any means. They're very still closely packed together. So water's liquid form is water. So you know what I mean? We're thinking about ice, how ice is a rigid structure that's packed tightly together. Those water molecules are still wiggling around in ice, but they're not doing what water's doing, the liquid water. They're not slipping and sliding around. You know, you can think about the difference between like actually having an ice cube and a glass of water. I can actually kind of manipulate those atoms and molecules a bit more in that water glass than I could with the ice. So again, the atoms and molecules, they're still touching, they're still interacting, but they are free to slide past each other and move around, and they're also always constantly wiggling. So liquids are a bit more loosey-goosey. So they take the shape of the container, you know what I mean? So when you pour a glass, you could pour water into lots of different shapes, different containers, and it matches the shape of the container. If I put it in that same Tupperware container the gold ring was in, well, then it would match the shape of the container. However, liquids don't expand to fill a container, right? So I always have the same volume of liquid, no matter what container I put it in. Even if it looks a little different, the shape has changed just a tiny bit. So solids are rigid. The molecules and atoms do not move. They are held in place, yet they wiggle a little bit in place. Liquids will have atoms and molecules that are still very closely packed together. You can see it down here in the picture. They're very tightly packed together. But they still have a bit more freedom of movement where they slip and slide past each other. They're not held in a specific position within the liquid, and liquids can therefore take the shape of their container. All right, last one here, we have gases. So gases are atoms and molecules that are separated by large distances, and they don't interact with each other. That's kind of a little bit of an assumption. We'll talk about why later this semester when we talk about gases. But we're going to assume they do not interact with each other and they're separated by very large distances. So gas atoms and molecules are kind of doing this. They're flying around everywhere. They're bouncing off the walls. They're going crazy. They're going places. They've got things to do. They're just changing directions by everything that they run into is how gases work. So it always makes me think of something like this. Like you're going real crazy, crazy arms going everywhere, okay? So we have our solids, we have our liquids, and we have our gases. So they're free to move however they wish because they are not close enough to each other to influence each other or interact with each other. So in a liquid and solid, there are forces that end up kind of holding those atoms and molecules together. Has a little bit to do with temperature, a little bit to do with forces. We'll talk about that, I believe, in part 3 of this lecture series. But they are, again, they're kind of held together, whereas a gas, whatever my left hand is doing, it has nothing to do with my right hand, for example, if I'm picturing them as an atom or molecule. And gases fill the shape of their container, just like liquids do. However, they can expand and contract their volume or their amount of space they take up. So the thing is that with a liquid, you know, you're not going to have water all of a sudden jump to the top of your container, the top of your water bottle or something like that. However, with a gas, it's going to fill every space that it can in the container. It's just going to move around and bounce off the walls of that container. So when something is able to take the shape of its container and fully fill that container and have that ability to expand and contract, they can get bigger in volume or smaller in volume. They can take up more space, take up less space. We call that compressibility. So a gas is compressible. It's the only state of matter that we're going to talk about in this class that's compressible. So solids and liquids, you're not changing the volume you have no matter what you do to them, but with a gas, you can change that amount of space that it takes up. So because gas atoms and molecules have so much space between them, when you're compressing them, you're just forcing them to be closer together and you're giving them less spaces to be between. So that's kind of what we're thinking about. Gases are, again, the wild ones flying around. Liquids slip and slide past each other, but they still touch each other. And solids are kind of held in place and they go wiggle, wiggle, wiggle. So that's going to be our states of matter. Again, we can kind of make a summary comparison here, and it's easy to see the difference in the placements of the molecules and atoms in the pictures down here. So this is a good slide to review if you want to triple check your understanding of the states of matter. So you should definitely keep an eye on this chart and be able to look at a picture like this and match it up to whether it's a solid, liquid, or gas. Or if I say, you know, I have atoms, they're very close together, but they can fill the shape of their container. It's not compressible, yet some of the atoms are so the atoms are still free to move relative to one another. Well, you should be able to know then that I'm describing a liquid, okay? All right, so let's talk a little bit about classifying matter according to composition. So what type of matter do you have? We have kind of 4 different categories here under 2 subcategories. I'll show you a flow chart. It kind of makes more sense, but I just got to kind of give you some definitions and talk a little bit of our way through this first. So another way to classify matter is to look at what it's made of, okay? So we were looking at how the atoms and molecules were located compared to each other in a solid, liquid, and a gas. But now when we're talking about classifying matter according to composition, we're looking at what actually type of atoms and molecules make up a substance. We kind of have a pure substance and a mixture as the 2 broadest categories that we can use to classify matter. So a pure substance is made up of only one type of atom or molecule. So a pure substance kind of makes sense. Pure substance, only one type of atom or molecule. And underneath pure substance, we have 2 different kinds of pure substances. So if you have a pure substance, you can have an element or you could have a compound. So an element is a substance that cannot be broken down into any smaller grouping. These are individual atoms, okay? So an element is what you see on the periodic table listed there. So that would be just one type of atom, and the periodic table, again, contains all the types of atoms that we know about currently. A compound is a substance made up of 2 or more elements. So these are molecules like water or table salt or sugar, and they're more common than elements because elements often naturally mix and react. So if I have all of one type of molecule, I have a pure substance, but it's a compound. If I have all of one type of atom, it's a pure substance, but it's an element rather than a compound. So, you know, compound, you always think about maybe putting things together, compound words or something like that. So you're thinking about, oh, I've got atoms hooked together, but you only have one type of molecule, for example. So it'd be like pure water, pure table salt, pure sugar kind of a deal. I only have one thing there, even though it's made up of different kinds of atoms all hooked together to form that one kind of molecule. So again, a pure substance is made up of only one type of atom. That would be an element. One type of molecule. That would be a compound. We also have mixtures. So if a pure substance is made up of only one type of atom or molecule, a mixture is made up of 2 or more types of atoms or molecules. So a mixture has 2 or more types of atoms or molecules. So this could be a homogeneous mixture. So we call that word right down here, homogeneous. I think you can also say it homogeneous, but I always said homogeneous. I think it's more fun to say. So that would be a homogeneous mixture. It's something that's mixed consistently all the way through. It doesn't matter where you take your sample from. It's going to be the same ratio of one type of atom or molecule to another. So you might think about salt water. Anywhere you go in the ocean, you're getting the same ratio of salt in the water, no matter where you're going to pull that water from in the same ocean, right? Of course, we have different things like the Dead Sea, where there's a really, really high amount of salt in the water. That's why people can float on the Dead Sea. But anywhere I go and I draw that sample of salt water from in the Dead Sea, I'm going to find that same homogeneous mixture, it all mixed all the way through. Just like blood or steel or brass, those are mixtures as well that are mixed like all the way through. When you're thinking about like heterogeneous, that would be the opposite of homogeneous. So if homogeneous is mixed all the way consistently through, heterogeneous means if I drew a sample from different pieces of a substance, I might find a different composition in different places. So it's not consistently mixed. It's like you got halfway through blending your McFlurry, and then you get to the bottom and you realize that they didn't mix it all the way through. So at the top of my McFlurry, I've got cookie pieces. At the bottom, no Oreos. So that's an example of like a heterogeneous mixture. So like oil and water. So like when you mix oil and water up, you might be able to kind of get it to look like it's mixed all the way through, but there are distinct areas of water, and you can see like kind of the oil bubbles floating through the water, and eventually they'll separate themselves out if you let it sit for long enough. So they're mixed, but their composition is varied by region. So if I like went to the top, I might get oil. If I went to the bottom, I might get water, for example. Pizza is a good example of a heterogeneous mixture. So when you take a bite, if you have like a supreme pizza, for example, you might take one bite, you might have some pepperoni, you might have some sausage, you might have a mushroom. You take another bite, you've got an olive, you've got a little bit more pepperoni. You take another bite, you're getting just cheese and sauce and bread. It kind of depends as you're working your way through that pizza what you're getting in each individual bite, and each individual bite might be different. So that would be an example of a heterogeneous mixture. You might also think of salad. You're taking a different bite of different things every time you take a bite of salad, or like Chex Mix, for example. It's got all the different things in there. They're all mixed up together, but, if I take a handful of the Chex Mix, maybe all of the pretzels have settled to the bottom, and I don't get the pretzels until I get to the bottom of the bag of Chex Mix. So those are some mixtures that are heterogeneous that you may have come in contact with. So again, we could have a homogeneous mixture, something that's mixed consistently all the way through. It's made of 2 or more types of atoms of molecule, but no matter where I draw a sample from, no matter where I look at, I have the same mixture consistently mixed all the way through. And then again, we can have heterogeneous mixtures. So again, 2 or more types of atoms or molecules, but it kind of depends where I draw the sample from what I'm going to see. So I really like that pizza example. So when you take a bite of pizza, you might get a different bite of something every single time. So again, we have pure substances. You can have an element with only one type of atom. You can have a compound with a pure substance compound with one type of molecule. You can have a mixture where you have 2 or more types of molecules that are consistently mixed through, which is homogeneous, or 2 or more types of atoms or molecules that are not mixed consistently, and that would be heterogeneous. So this is kind of a visual example of a pure substance. So again, they can be made of elements or compounds as long as it's only one type of thing. So here you can see we have some helium balloons. So these are helium atoms represented as a gas bouncing around, but because they're all the same color, they are considered to be the same atom in our picture here, so we can see that we only have one type of atom represented. As far as compounds go, here you can see that I have different molecules. Remember this water molecule, these space-filling models. So you can see we still have 2 hydrogen atoms, 1 oxygen atom, and every single one of those molecules is made up of 2 hydrogen atoms and 1 oxygen atom. So I can see that I have all of the same things here together, but they are, so they're molecules, so they have more than one type of atom, but they're all the same molecule. So here I have a pure substance element, and here I have a pure substance molecule, or I'm sorry, pure substance compound. I'm missing a slide. That's okay though, we can look at these pictures down here. So we can also see with the homogeneous and heterogeneous mixtures, here I have different kinds of molecules. You can see that there are some water molecules, some sugar molecules, and some tea molecules in there. So it's mixed consistently all the way through. No matter where in my tea I check it out, I'm probably getting the same amount of sugar and same amount of tea and same amount of water in the end. But if I look at this oil and water mixture over here, I can see that I have oil molecules at the top and water molecules at the bottom. So if I tried to get a sample and I took it only from the bottom, I would just get water. But from that same overall glass, I could get a sample from the top and only get oil. So you can see that they're not mixing with each other. Whereas over here, it's all mixed and all consistent. So let's go ahead, let's work through some examples. It can be really beneficial. I'm gonna do just the first few here as examples. And then it could be beneficial for you to work your way through the rest of them and kind of quiz yourself and check with the answers that are on the last slide. So if I'm thinking about nitrogen gas and I want to follow my flow chart here, what the flow chart reminds you is that if you have matter, matter can be split into pure substances and into mixtures. So pure substances, remember those only have one type of atom or molecule, and mixtures have more than one type of atom or molecule. So if I have just nitrogen gas, it's matter. It's a gas, it's matter. It's nitrogen, it's matter. It matters. So anyways, I have to decide whether nitrogen gas is a pure substance or if it's a mixture. If it just says nitrogen gas, I can assume it's a pure substance. It's only nitrogen atoms. So pure substance here, nitrogen atoms and my nitrogen gas. And then I have to decide, is it an element or is it a compound? So is it made up of one type of atom or is it made up of one type of molecule? Well, if it's just nitrogen, that should be an element. It's only one thing. So it's going to be a pure substance than an element. Okay, so nitrogen is an element. Brass is a mixture of copper and zinc atoms. So it's a consistent mixture of copper and zinc atoms. So if I'm following my chart, I know that I have to decide whether it's a pure substance or I decide whether it's a mixture. So brass is a mixture. And then I have to decide, is it mixed the same all the way through, or is it mixed differently in different places? So you might think about like a trumpet or some sort of brass instrument in this case. That's why they're called brass instruments, or the brass section. It's because their instruments are made of brass. So if I'm thinking about that, my trumpet doesn't look different anywhere there's brass on that trumpet. It's mixed the same all the way through. So here I have brass, which I know is a mixture of copper and zinc, but it's going to be a consistent mixture all the way through, so we're going to consider brass to be homogeneous. So besides just thinking about atoms and molecules, we can kind of classify things in a larger scale. For example, like we could do an example here, like cereal in milk, okay? If I'm thinking about cereal and milk, if I'm eating my cereal, there are places that have my Cinnamon Toast Crunch in it. There are places in the water that the water, I do not eat my cereal with water, with milk. So I'm eating my cereal with milk. There might be places where that milk has dissolved some of that cinnamon sugar that's fallen off. Some of the pieces are going to have more cinnamon sugar on them. Some of them aren't. Some of the pieces are going to be dry and haven't gotten into the milk yet. Some of them are going to be soggy because they've gotten into the milk. If I really wanted to, I could take my spoon and just scoop milk out of there if I wanted to. So if I'm thinking about how I would classify that as a state of matter, obviously cereal is going to be a mixture. You know, we just kind of talked about that. It's milk and it's some sort of cereal. In this case, in my head, Cinnamon Toast Crunch. And then from there, I need to decide whether it's homogeneous, it's mixed the same all the way through, or if it's heterogeneous, and I have different things going on. By my description, as I've thought through this process, I'm going to classify that as heterogeneous because there were lots of different pieces to that mixture of cereal and water that were very different from each other, very different experiences when you're at the very start of your cereal versus the end of the bowl. So those are kinds of some examples of how we can work through this flow chart. Again, it would be really good if you practiced and you kind of went through, did all of those on your own, the rest of the examples here. So that is how we classify matter. That's what matter is. Remember, we can classify it as a solid, liquid, or gas, and we can classify it by also what it's made up of. And in the end, matter is anything that takes up space and has some sort of mass to it. It has some sort of oomph to it. So that is part 1 of chapter 3. Be looking out for part 2 and part 3 coming up.